So the beta function, it turns out, is closely related to the gamma function. It's not obvious from the definition, but we'll see a bit later why. Again, this integral only exists for real a and real b greater than 0, but it can be defined for other values of a and b using a formula we'll come to shortly. So it's symmetrical in the arguments a and b, which is easy to see by this substitution. Another substitution gives us this alternative form for it in terms of powers of sine and cos. Yes, another substitution gives us this. So we see it's actually quite a useful special function for dealing with what look like fairly simple integrands, but because a and b can be fractions, or then these would normally be difficult integrals to do, and you need a special function to give you an answer in closed form. And then finally, this sort of alternative definition of the beta function in terms of the gamma function. So this we're going to prove because it is actually quite an interesting formula to prove. The proof is rather similar to the proof of the integral of a Gaussian, e to the minus x squared, as you'll see if you've seen that proof before. So make the substitution u equals x squared and v equals x squared. Okay, I should have said make the substitution, as you can see, into gamma functions. So we're basically starting with gamma a, gamma b, and we're multiplying them together, and we've got one variable which is u, another variable which is v. We're making the substitution x squared and y squared. Now the reason for doing this will become obvious. We then combine this as a double integral, which we're allowed to do because u and v are separate. And then the clever trick is to change variable. So we change variable from Cartesian coordinates x, y to polar coordinates r cos theta, r sine theta, which is what's happening here. And obviously the integral in the xy plane is the first quadrant. X and y are both greater or equal to 0. So if we convert that into polar coordinates, that basically means r goes from 0 to infinity and theta goes from 0 to pi by 2. Okay, then we realize that we can write with a change of variables t equals r squared. We can rewrite this in terms of the gamma function. Because this becomes this, which you can express in terms of the gamma function, gamma of a plus b. And this here we recognize as one form of the beta function. So we end up with beta ab times gamma ab equals that. So knowing how the beta function is related to the gamma function allows us then to come up with relations like this. We can relate beta of the argument plus 1 to beta of AB and so on, using this definition and the rule for gamma functions, this rule for gamma functions here.